Good morning, everybody. Today, we are going to talk about aqueous reactions and aqueous solutions. So, aqueous, new vocab word perhaps. Actually, not really, because we talked about it with naming acids. It means dissolved in water. So, we're going to see that reactions that are taking place in water can be a little bit more complex than the reactions we've talked about so far. And we're going to see that the kind of reason that they're able to react is because they're in solution. So we know that putting two solids together doesn't really work. The reason for that is solid atoms are just kind of vibing in place. They don't really move. And so we can't really react two solids together. But if we dissolve them in solution, often that solvent is water. Water is a liquid. Liquids move around, right? Liquid molecules can kind of move past each other. And so as a result, that can help us bring solid bits together that can react. And so we're going to see that this is a great way to kind of get past that problem. In previous things we saw, okay, like with a combination, I could take two gases and put them together. I could put a gas and a liquid together, something like that, where we can have nice things that are already moving. But solids can't do that by themselves. So we need to bring them into solution in order to get them to be able to react together. And so it makes sense that the first thing we should do is talk about what dissolving means. And so we're going to see that many compounds that we deal with here can dissolve in water. And we've talked about many different kinds of compounds so far. We've talked about ionic compounds. We've talked about covalent or molecular compounds. I'm going to write molecular. And we've talked about acids as well. We've talked about three different types of compounds. Ionic compounds, when they dissolve, will separate into their ions if they're soluble. They will separate completely into ions. And we'll take a look at what that's going to look like. And we'll learn rules for solubility of ionic compounds. So if an ionic compound dissolves in water, it's going to separate into its ions. And we'll take a look at that in a little bit. If a molecular compound is soluble, it will exist as a molecule still. Meaning there's no separation of anything that's happening. It's just dissolved. It will still exist as a molecule there. And acids, we're going to see, are always soluble, but sometimes break into ions. So acids are going to kind of be our middle ground here. So let's talk about all of these kind of one by one. Let's look at ionic solids first, or ionic compounds. Generally, they're solids. Ionic compounds, let's take our favorite sodium chloride. Okay, I'm just going to draw two rows of this stuff because it's all the same. we're going to see that when sodium chloride dissolves, what ends up happening is we're going to have water molecules surrounding those ions. So we're going to talk about why that is later when we talk about polarity, but water is going to be surrounding all of these ions. So we'll have split our ionic solid up into positive and negative bits. So let's say the greens were the negatives, the blues are the positives. We're going to see an ionic solid like that. Remember, things are kind of alternating in a solid like that. When they separate, they become just kind of individual ions. So if we were to take sodium chloride and dissolve it, you would get sodium ions and chlorine ions. And those states of matter would be aqueous. So if you take a solid piece of sodium chloride, put some water with it, you'll end up breaking it into sodium and chloride ions. And they'll just be surrounded by the water molecules. That's going to help break those apart. Notice if you did something like calcium chloride, dissolve that in water, you would break that into a calcium 2+ ion and 2 chloride ions. Right? There's a subscript there. That subscript is for charge balancing. It tells us we have 2 chlorides to balance out the calcium's 2+ charge. So don't forget that when these things dissolve, you still have to take into account the numbers. We do not have this. That is a no-no. We do not have some sort of mystical Cl2 2- business. Does not happen that way. So it's always going to separate into the ions that made it up to begin with. So when we talked about naming ionic compounds, we did all this charge balancing. We saw what ions things are made of. We saw their preferred charges and all that. And so it's going to be the same idea here. It works with polyatomic ions too. If we had barium hydroxide, apparently I'm using blue this time, but we'd have the same idea. Your polyatomic ions still stay as their polyatomic ions here. So we don't separate that into oxygens and hydrogens. It stays as the polyatomic ion. It was the hydroxide. One more thing, because ions conduct electricity in water, which is why it's a bad idea to be at the ocean if there's a lightning storm. If you have to be in water, choose fresh water, but ions conduct electricity much better than pure water does. And so we will often call these soluble ionic compounds, strong electrolytes. Electrolytes comes from, I don't know, Greek maybe. Electro means electricity for us. Light comes from lysis, which is breaking. So we're looking at something that breaks and conducts electricity, and that's what ionic compounds do. And they do so strongly. They strongly conduct electricity. So we're going to see here that those are called strong electrolytes. And I have totally not prepared the video for this. Let me just see if I can quickly find one on YouTube on electrolytes so you can see it. Where's the freaking electricity. This is all like random people trying to sell me stuff about collagen. All right, I'll show you the video later. I'll show it to you on Thursday. I'll have it prepared for you. But suffice it to say, solutions of ionic compounds conduct electricity very strongly if those are soluble. We're going to see some ionic compounds don't dissolve at all. Many of those ionic compounds form rocks. Rocks don't typically dissolve very well. Chalk is another ionic compound, doesn't dissolve. So it has to be soluble for it to be a strong electrolyte. All right, and we're going to see that we're going to learn rules for ionic solubility. So for right now, we're going to call those strong electrolytes. All right, let's look at molecular compounds. If we take sugar and dissolve it, this isn't sugar, this is glucose, or fructose or whatever, one of your sugars, we still keep the same molecule. It just becomes dissolved. So we're taking now molecules that are kind of just chilling out together as solids, and we are now going to surround those by water, but there's no charges or anything happening here. We're going to see that they just dissolve. So we just have them surrounded by water, and that just helps them to dissolve. However, they don't break apart into anything. And because of that, a sugar solution like this conducts electricity just as well as plain old water does. So nothing new. It doesn't add anything to the water in terms of conductivity. And so we'll call these non-electrolytes. They do not, what we call, dissociate. Associate means coming together, right? And dissociate would be breaking apart. So non-electrolytes, which are going to be molecular compounds that are soluble, are non-electrolytes. They do not dissociate. So they just become dissolved. They're surrounded by water, but they don't form any ions. There's nothing special happening here. They just kind of dissolve. They separate off the rest of the solid and just go and do their own thing. So those are going to be soluble molecular compounds. All right, and then with acids, we're going to see some acids will indeed behave like ionic compounds and separate completely. But some other acids are actually going to just do this just to a very slight extent. For acetic acid, that's about 1%. Will actually ionize. And so here we can introduce some classifications of acids. We're going to see that we have 6 strong acids. I'll write them out here in, how about purple? No, why not? We've got 6 strong acids. These ones will completely dissociate in solution. And therefore they are acting as ionic compounds. And so these ones are strong electrolytes. Those acids will completely break up into their ions. So that's why HCl will break up completely into H plus and Cl minus. And it's going to then conduct electricity because those have completely broken up. Most acids, though, are not strong acids. Only those 6 are strong acids. And the rest of the acids only dissociate a little bit. So maybe at any given time, 1% of acetic acid molecules have actually split up into ions. All right, whereas 100% of HCl's would have. And 0% of sugars would have. So we see these are much more similar to the non-electrolytes, but since they do ionize a little bit, we have a special term for them. All other acids are weak acids, and they are weak electrolytes. Because they only break apart a little bit. They only dissociate a little bit. You'll learn how to calculate how much that is that they dissociate next semester. But suffice it to say now, learn those 6 strong acids. Those ones are strong electrolytes. Every other acid is a weak acid and is a weak electrolyte. It behaves more like a molecular compound than an ionic compound, but it's still kind of in between. So they conduct electricity slightly better than pure water does, weak acids, but not nearly as well as something that has an ionic compound or a strong acid. So those are weak electrolytes. And it's important we note as well that when we say strong and weak, that has nothing to do with how soluble something is. It has nothing to do with how concentrated something is, how much we've dissolved in there. It's all about the nature of the chemical compound. That's what determines if something is strong or weak. We have 6 strong acids. All other acids, the millions of other acids that exist, those are weak acids for us. Okay, so let's just put this down. The terms strong and weak have no effect on solubility or on concentration. So concentration is how much is dissolved, right? So you can have a lot of acetic acid dissolved in water, and it's still not going to conduct electricity as even just a little bit of hydrochloric acid. So the concentration, how much is dissolved, doesn't matter when we call something strong or weak. It's all about the nature of the compound. These terms are based on the nature of the chemical compound. So it's a lot can be a little bit hard to internalize because of that, but trust me, it's not bad. I'll show you a video on Thursday about that. So we'll see that this is just kind of how things dissolve. All right, so are there any questions on kind of like the dissolution idea of how things are dissolving in water? So we have 3 different types, right? We have strong electrolytes completely dissociate into ions. Non-electrolytes do not dissociate at all into ions. And then we have the weak electrolytes, which are kind of in between, dissociate a little bit. So typically we still will write them as molecules rather than ions. Alrighty then. Let's talk about some things. So how do we know if an ionic compound is soluble. I have rules for you. And you'll also see that sometimes people use solubility charts where they will correlate a cation and an anion and see if it will be soluble or not. That's fine. You're welcome to use a solubility chart. But oftentimes, we're going to see that there are some general patterns we can make out. So, a compound will be soluble if, number one, any of these three rules can apply. If any of these ions are present, your compound will be soluble. So anything that has any of these ions will always be soluble in water. So anything with sodium, lithium, potassium, rubidium, ammonium, acetate, or nitrate will always be soluble. No exceptions. Number two, if it has a halide, halides being non-fluorines, essentially. So halides, halogens that are ions, except fluorine. Fluorine does a few weird things, so we're just going to kind of not worry about fluorine right now. But those three halogens, anything that has one of these halogen ions, will be soluble with a few exceptions. These three exceptions are insoluble. They're in red for insoluble. So that could be AgCl, AgBr, AgI, PbI2, PbCl2. X can be any of those three halogens. However, everything else, if it has X, is soluble. So if you have Cl-, generally your compound will be soluble. There are three exceptions. Silver, mercury 1, and lead are all insoluble with halides. All right, and then our last kind of soluble one is if we have the sulfate ion. If in your compound you have sulfate, generally it will be soluble. We have a few exceptions here. So we have three new ones. Calcium, barium, and strontium sulfates are insoluble. And then we can go ahead and put our previous ones. our lead, mercury, and silver will also be insoluble with sulfate. These ones are all insoluble. The rules tell us what is soluble. So anything that has sodium, lithium, potassium, rubidium, ammonium, acetate, or nitrate will always be soluble. No exceptions. Things will be soluble if they have X minus as part of their compound, as long as those things are not silver, mercury 1, or lead ions of those. Everything with sulfate should be soluble unless it's one of these 6 exceptions. And notice 3 of the exceptions here are the same as the exceptions for number 2. So anything that's not here is generally regarded as insoluble. So 3 rules for things that are soluble, and we're going to assume that everything else is insoluble. With those rules, we do have a few exceptions. So, if we want to do a couple of examples, we can look at some of these. What else should we have? And let's do one more. Okay. With these compounds, let's use our rules to predict whether they are soluble or not. Let's see. What's going to be soluble and what's not here? We can go through them. So our first one, sodium carbonate. We probably want to reference our rules. So which rule of these is going to be most applicable here? Well, hopefully we'll see it's number 1. Anything that has sodium will always be soluble. So, yes, this one will be soluble. Do we see that? Has sodium in it, always soluble. Do we have any other sodiums on here? No. But if we did, we could circle those as well. Let's look at now lead 2 acetate. All right, let's look up at our rules. Which rule are we going to be looking at here? Well, 2 and 3 don't apply because we don't have X minus or sulfate. Let's look at rule 1. Aha, we do have acetate here as one of our ions that makes things soluble. So indeed, this one will also be soluble. Anything with acetate is soluble. Doesn't matter what it is. Next, calcium bromide. Let's go up to the rules. We're looking here generally at now bromide, so that's going to be rule number 2, something with X minus. We see that calcium is not an exception. It doesn't matter if it has lead in it. Anything with any of these in rule number 1 will always be soluble. I don't see an exception here that says lead 2 acetate. So it doesn't matter what else you've got. As long as you have any of these things in number 1, you'll be soluble. Silver nitrate, silver acetate, doesn't matter, calcium acetate. Anything that has any of these in number 1 does not matter what the rest of your molecule is. So a compound will be soluble if any of those ions are in the compound. That's the end of it. No more discussion. Anything that's got one of these, always soluble. Always, always, always. Okay? So anyways, with this calcium bromide, we're looking at, okay, does this have, it's got bromine, that's rule 2. Rule 2 covers bromides. Bromine is present, and calcium is not one of the exceptions here. There are 3 exceptions. Calcium is not one of them. So it's going to be soluble. These rules are telling us when something is soluble. So anytime we have X minus, we're looking at it's probably going to be soluble. But we have a few exceptions. Calcium is not one of them. So we are expecting this to be soluble as well. Cobalt 2 sulfate. Let's go ahead and look at our rules. Aha, we have a rule for sulfates. Generally, sulfates are soluble, but we have a few exceptions. Do we have cobalt as one of these? Calcium, barium, strontium, silver, mercury 1, lead 2. Those are the exceptions. Cobalt is not an exception. So therefore, cobalt 2 sulfate should be soluble because it's got the sulfate. Most sulfates are soluble. And indeed, we're going to see manganese 2 sulfate is not an exception either. It's got a sulfate. It's going to be soluble. Not an exception. All right, let's look at magnesium carbonate then. All right, let's go up. Let's see our rules. Well, I'm not seeing a rule for magnesium. I'm not seeing a rule for carbonate either. And so, anything that's not listed, we do not have a rule for, we will consider insoluble. So anything that's not listed is probably insoluble. So, because we have no rule for magnesium, we have no rule for carbonate, we're going to see that that's going to be insoluble. Alrighty. Next, ammonium sulfide. Let's scroll up to our rules. Do we have a rule for sulfides? We don't, but we have a rule for ammonium. Anything that has ammonium will be soluble. End of discussion. We have ammonium here. It's soluble. No thinking necessary. It's got ammonium. It's soluble. Mercury 1 nitrate is next. Mercury 1 nitrate, let's go ahead and look. Do we have a rule for mercury? Nope. Mercury is an exception for certain rules, but there's no rule for mercury. Do we have a rule for nitrate? Aha, we do. Rule 1. Nitrate there, the very last ion. anything with nitrate will be soluble. Does not matter that mercury is an exception for the other two. That's not relevant. We don't have a halide, we don't have sulfate with mercury. We have nitrate. So nitrate's rule will cover this. These rules are not contradictory either, right? They might be supportive, like sodium chloride is both rules 1 and 2. Anything with sodium will be soluble. Most things with chloride will be soluble. There's no contradiction there. Anything with nitrate will be soluble. There's no exceptions. It doesn't say right there lead nitrate is not soluble. It certainly is. It certainly is soluble. Anything with any of the rule 1 ones will always be soluble. For rules 2 and 3, most things are soluble, with a few exceptions. All right, some people do this as like 6 different rules, and it's like way too much. With the exceptions, they still have all that. So it can be tough. But these rules don't contradict each other. So always follow whichever rule is applicable. If no rule is applicable, it's insoluble. That's the case of the magnesium carbonate. We saw that that one is insoluble because we don't have a rule for magnesium. We don't have a rule for carbonate. So it's insoluble. Our rules tell us what is soluble. All right. Silver iodide. Iodides fall under rule 2. I minus. Generally, things with I minus are soluble, but silver halides are an exception. Silver halides are insoluble. So we're going to say, okay, AgI we expect to be insoluble. And so it's just a matter of practice with these. Learning the rules and learning how to apply them. Let me open a new window here. Oops, I need incognito. But some people really like solubility charts. Like this. I'll show you one. Here's a solubility chart. Some people like these things. And so a lot of people like kind of these things here. So with these, we're kind of looking at combinations of cations on the top here and anions on the left. We see, for example, all of our nitrates are always soluble. So that's the rule. It's a little easier. All the ammoniums, apparently lithium phosphate's insoluble. I didn't know that. But generally, these 4 ions that we put there are always soluble. If we look at our acetates are soluble. Our nitrates are soluble. Our sulfates and halides are mostly soluble with a few exceptions. Like we have silver as an exception to many things. Lead as an exception to many things. So you can use a chart like this if you really want, but it may not cover everything. Like there's no mercury on this chart, but there may be on a different chart. Like let's look at this one. What does this one have? Chromates and let's see, what else do we have? Nitrate, hydroxide. We don't have mercury on this one either, but we have nickel, go figure. So there's all these sorts of charts. You could have all these sorts of rules as well. So here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rules with exceptions. So a little bit tougher to work with, right? And like they're the opposite of each other. It's like, all the exceptions are alkali metals for all these, or ammonium. But instead of putting them always as exceptions, it may just be easier to say, well, let's just make everything with those soluble. So yeah. Same thing here. You can have your ions. You've got solubility. These are always soluble. Always soluble. So That's the thing, is unfortunately with all these charts, some will cover certain things, some will cover others. It's probably easier to just use the rules. But if you want to use a chart, go right ahead. Just know your chart may not cover all of these things. The rules should cover everything. Everything that's not covered is insoluble. There are some slight exceptions that are minor. Because I want to keep everything concise, as short as possible, so that it makes it easier on you to reference, there are a few exceptions that are very minor. Like there are a few sulfides, like maybe calcium sulfide is soluble, but that's minor. That's one like extra compound. And it doesn't justify then making a rule for sulfides, because sulfides would have so many exceptions. And calcium has a lot of exceptions too, so it doesn't really make sense to have a rule for calcium. So I am very happy for you to say anything that's not in a rule is insoluble. I'm okay with that. The few exceptions, whatever. Let's not worry about them. The rules will cover everything for this class. All right. Anything that doesn't have a rule is not applicable with any of these, we're going to say is insoluble. All right. So maybe a good idea to practice some of that. There will be a homework on this, of course, that you'll work on. But we're going to see that this is going to be an important consideration when we talk about ionic reactions, is determining if something is soluble or not. So it's time to introduce our next reaction type. Which are called double displacement reactions. Also known as metathesis reactions, but that's less common of a word. Double displacement works just fine. Double displacement reactions are essentially combining two ionic compounds that are in solution, and we end up switching their partners. So we now have A with Y and B with X. So we end up pairing off the opposite. So the cation from one compound goes with the anion of the other compound. They're switching partners. That's all that happens here. Notice that we don't get these ones, because remember, in an ionic compound, the cation, the positive one, always comes first. So that means A and B are cations, X and Y are anions. We're not going to put two negative ions together. It doesn't make sense. We're not going to put two positive ions together. So it doesn't make sense to do that either. So here, A and B are cations. That means positive. And X and Y are anions, which means they are negative. So we switch our two. A used to be with X, now it's with Y. Switch the anions. B used to be with Y, now B's with X. We switched our anions. Or you could consider it switching the cations, like either way. So it's simply a matter of swapping them. Here's an example. If we want to predict the products of this reaction, we might be tempted. Okay, let's just switch them. Whoops. I put these in red for a reason. What's wrong with what I did? How did I mess this up? Something's wrong with all these. The order? I could put CaNO3 first if I wanted. These aren't charge bonds. These are compounds that don't exist. AgCl2? Ag only makes positive ions. Chlorine only makes negative ions. So if I have AgCl2, that's not neutral. Calcium nitrate has 2 nitrates. It doesn't have 1. So this is a big old no-no. It doesn't matter which one you put. If you put, I mean, it's positive, so or it's a plus. So there's no like you can put it this way. This doesn't change anything. We still have our 2 products, but the products are wrong. That's the problem here. So remember in math, 1 plus 3 is the same thing as 3 plus 1. We can change the order of them. It doesn't matter. So, good guess, but not what we're looking at here. So these aren't charge balanced properly. If you look at the ions that make up this, the ions that make up these compounds. Oh. So remember, positive ones always come first. So your metal will always come first in your ion. The positive ion comes first. So Cl2, if we put that in front, that means we're putting the negative one first, which is a no-no. So always we have to put our positive one first. So that's why we could say Bx plus Ay, but still it's got to be Bx and Ay. We can't say Ya and Xb. Always those have to be in that order. So, if we look at the ions that make these up, we're going to see how we mess this up. We ended up putting, when we do this, we need to switch the ions, right? We're going to take the positive from one and the negative from the other. And we're going to put those together. I'm in fact going to write these ones in a different color just so we see they came from a different compound. So that's why it's very important that we know how to charge balance things. It's very important that we know our polyatomic ions and know what charges they have and our preferred charges of many of these elements. So if we're going to take one purple thing and one blue thing, positive from one, negative from the other, we can say that we can take the calcium first. Why not? We want to be putting together calcium and nitrate. If we make a compound out of that, that becomes calcium nitrate written as such, where we have now the perfect charge balanced compound. And if we take the other part, if we take our other purple one, the positive purple one and the negative blue one, if we charge balance that, they're the same charge, so we just need to write AgCl. Always positive one first. Excuse me. So these are the correct compounds for our reaction. So if we rewrite it, the compounds we're making are AgCl and calcium nitrate. So silver chloride and calcium nitrate. We swapped the ions, and we've charge balanced properly. Remember that this 2 here, this came from charge balancing with the calcium. That's where that 2 comes from. That 2 is not inherent in chlorine. Right? There's no Cl2 2- polyatomic ion. That 2 comes from charge balancing. And so we don't care about that. We care about what ions are present here. We don't have Cl2 2- ions. We have 2 Cl- ions. Remember, if we break this guy up, if we dissolve it, we get calcium and 2 individual chloride ions. We do not get some weird polyatomic thing like that. Nope. We always have to remember the preferred charges of our ions and our polyatomic ions. So we have 2 things to remember: preferred charges, polyatomic ions. Those things don't change. We don't change those. Here, at least. We'll learn next time how to change those, or when to change those. But what's important here is you look at the ions that make up your reactants, switch the pairs, and charge balance properly. So the 2 that's part of that subscript for chlorine does not have any impact on what happens in our reactant side. All chlorines in ionic compounds are Cl-, unless it's part of a polyatomic ion. But chlorine by itself is always Cl-. Chlorine doesn't have any other option. And silver is always 1+, right? So to have AgCl2 makes no sense. We have 1+ and 2 minuses. So that's not a real compound. That would be some sort of ion or something. Doesn't exist. All right. Well, we're going to look at this again in another example, but I want to finish off this one. So now that we have our reaction, our reactants are going to be aqueous, right? I've given that as a kind of condition of this reaction. We have 2 aqueous ionic compounds putting them together. We're going to see that we can predict the state of matter of our products. And so this is when we're going to refer to our solubility rules. We're going to see that if we look up silver chloride, let's go up to our solubility rules, find our rules for silver or chloride. We don't have a rule for silver, but we do have a rule for chloride. That's rule 2, X minus. Aha, we see silver is an exception to normal chloride solubility. And so silver chloride should be, therefore, insoluble. And so in our reaction, get this, we will put that it is solid. It is insoluble, which unfortunately carries the letter S for solid. If something doesn't dissolve, it's going to stay as a solid. If you put a piece of chalk in water, which is calcium carbonate, if you just put a piece of chalk in water, it doesn't dissolve. It stays solid. Doesn't dissolve. So we're going to keep the S there. S indicates solid. Solids are insoluble. And if we want to look up calcium nitrate and see what we expect that one to do, We can go back up, look for calcium nitrate on this chart of stuff. Do we see a rule for either calcium or nitrate? Indeed, we see rule 1 is nitrates. All nitrates are always soluble, no matter what, even if there's lead, as someone mentioned earlier. So, anything with nitrate is always soluble. So, things that are soluble are dissolved in water, which we call aqueous. So we will indicate AQ for those. All right. So we see here that we're mixing two solutions, two aqueous components, and we're getting out of this reaction a solid, something solid. This is called these are called precipitation. So we're forming a solid in this. And often what that looks like is, since we're forming kind of just particles of solids, it just will look cloudy. Let's see if I've got a nice video for this. Okay, you know what I do? I'm going to go ahead and find our video because it's a good one. I am so proud of my video. Let me just, apparently, oh, I forgot the www. That's so stupid. It's weird that, like, sometimes websites still make you www. It's like, nobody does that anymore. Okay, let me pull this up here. Put it up. So I wrote a textbook for 101. I'm sorry, for what? Yeah, for 101 for this college. And so I have a bunch of videos that I've made of me doing fun things. So let's go ahead and take a look at what this looks like. So I'm going to go ahead and switch windows here. We're going to look at a precipitation reaction. Is this the precipitation? Yeah, so it is. So in this case, it's a different set of reagents. But we have here two clear solutions, right? I'm going to mix them together. Do some time-lapse fun here. I've formed a bright yellow solid. How do I know it's solid? Is because of that cloudiness. Those are individual particles of, in this case, lead to iodide. We can't see through it. It's cloudy. That's particles. And if we were to let this settle out later, we would see that those particles would fall on the bottom, and we can see very clearly it's a solid. So let's see that again. Where's my little cursor? Okay. So again, two clear things, ionic compounds in solution. Putting them together, I'm forming a solid. The solid is little granules, which appears to us as cloudiness. Sometimes it's white cloudiness, sometimes it's, in this case, yellow, because lead iodide happens to be yellow. Since we're here, we can look at a few other types that we'll talk about. Notice, I want you to look at the thermometer. We're looking at about 21, 22 degrees here. Let's see what happens when we put these together. This will be what's called a neutralization reaction. Look what's happening to the temperature. Look at all that steam we see and the little bubbles. So this one will end up producing a lot of heat as we go through it. That's called a neutralization. So we'll see that, and we'll talk about that one later. Also because it's just acid base. Here's one that you've done at home, perhaps. Let's see what happens when we put these two together. In this case, we formed a gas. This is vinegar and baking soda. You've done this one. This is your volcano experiment. So again, mixing two solutions of, well, in this case we have an acid and ionic compound, but We are making a gas. That's evidenced by those bubbles. And the last one is the coolest, perhaps. I've got an ionic compound and a solid here. We're going to time-lapse this one. And let's see what happens. Very interesting things happen. We've got little bits of crystals forming. And the solution has turned blue. So we've got all those little bits on it. That would be a nice precipitation, right? We formed a solid. Now it's coating our copper. And if we look at that solution, here it comes. It's blue. So color changing. That's another interesting reaction evidence that we have. So that is, those are a couple of examples of evidence. Let me see if I can actually find that electrolytes video as well. Where would that be? Solutions, duh. Okay. All right, let me just find this video for us so we can talk about the electrolytes. Since I have it up now. Is this my electrolyte video? Yes, it is. So, here we've got some conductivity stuff happening. We're going to see how well these things conduct electricity. So, we're going to see that the big light bulb is for lots of conductivity. The small light bulb is for minimal conductivity. So we're going to see what happens. So I've got deionized water here. That means pure water. Skipping ahead, blah, blah, blah. You don't need to see me explaining the light bulbs. And I'm just going to rinse the electrode in the big beaker back there. But here we go. Let's see what happens. DI water, no conductivity. And yes, that is indeed Superintendent Chalmers, who I use as my electrode here. If we look at tap water, we have some ions present there in the tap water. But we try to switch that to the superconductivity, and it's kind of minimal. So we have some small amount of ions there. If we try the sugar water, no conductivity at all. Sodium chloride water, we definitely have some conductivity. Let's check the big one. Superconductivity. So we see that sodium chloride there, a soluble ionic compound, will give us conductivity. Calcium carbonate, also ionic, but not soluble. Therefore, no ions are present in solution. So there's our evidence. We saw that the sodium chloride gave us the biggest conductivity, and the tap water had just kind of some minor conductivity, just because there's some ions in the tap water. But sugar, calcium carbonate, and DI water did not. If we want to look at the acids, let's see. No, that's not that video. I'm going to have this video for us here. Conductivity part 2. So, these are concentrations, these numbers here. Suffice it to say, we're just looking at HCl, a strong acid, acetic acid, a weak acid. We're going to be looking at the same kind of things here. We can skip ahead. Where's the fun part? So this time we're going to introduce the medium light. That's for our weak electrolytes. All right, let's see what's going to happen here. So tap water, as we know, or DI water, as we know, does not have conductivity. Let's take a look at hydrochloric acid. Definitely a small amount. Definitely medium amount. And definitely large amount. So ions are present there. A lot of ions. Let's look at the acetic acid. Same concentration. We got some minor conductivity. Let's check the medium light bulb. We have just a very, very slight amount. You can see that light bulb is struggling to exist. And if we try the big one, we're not going to get it. So evidence again that we don't have complete ionization of that acetic acid. And even if we have dilute HCl, we're going to see here definitely there. And let's check the big one now. We even have the big one. So concentration doesn't matter with these. We'll talk about concentration later, but it doesn't matter. All about the identity of your compound. So there we go. That is our video exploration for the day. All of those are mine. I did so well. My acting is impeccable, as you can tell. So anyways, this precipitation reaction was the cloudiness that formed. For that reaction, that was potassium iodide and lead 2 nitrate for lead 2 iodide and potassium nitrate. These were both aqueous, clear solutions. We saw that we got a solid out, which was our bright yellow cloudiness. That was our lead 2 iodide. Silver chloride that we had in the previous one is a white solid, so we would have seen that forming. Instead of a yellow one, we'd see a white cloudiness happening there. And so that's silver chloride. Notice again, I've done the products for us here, but our products always are charge balanced properly. You deal with the fact that there are 2 nitrates when it comes to balancing the equation. That's when we worry about the nitrates. If we were to balance this, we would see, aha, so we do have 2 nitrates on the right, but they're kind of separate units, whereas they were still part of the same lead 2 iodide, lead 2 nitrate before. So balancing is when we can fix all that stuff. When you're predicting the products, we only look at the ions themselves. Okay, so we only look at the ions themselves there. Let's do another one. Let's try and figure out the products of this one. If we want to figure out the products, we have to think of what ions are present here. In this, we know sulfate has a 2- charge. Since we have the same amount of cobalts and sulfates, we know that the cobalt must be 2+. Remember, cobalt is a transition metal, so it could do different things. I have it as 2+ here. Here, we know this is made of sodium and carbonate. So if we are to mix these two to switch things, positive from one goes with negative of the other. So we're going to need to mix cobalt and carbonate. They have the same charge but opposite sign. So we can just put that down. Next, we have sodium, which is +1, and sulfate, which is -2. We're going to need 2 sodiums to balance out the sulfate. So you want to take your ions, switch their partners, and form the new compounds. In this case, everything's already balanced. We're already happy with that, so this worked out nicely. We're going to want to now go ahead and figure out the solubility. Let's check of cobalt 2 carbonate. Let's see what happens with that. All the way up. Do we have a rule for cobalt 2+ anywhere? Not one of our 3 rules. Do we have a rule for carbonate anywhere? We do not. So, no rule means insoluble. Insoluble we write as S. Solid. With sodium sulfate, we have sodium there. We don't need to think about it. Anything with sodium is always soluble. Most sulfates are also soluble, but that's redundant. Sodium is enough to get us to say it's soluble. And so this is also a precipitation reaction. All right, already balanced, so we're good there. But we want to get in the balance, or the pattern of identify the reaction type. These are all double displacements because we're putting two aqueous ionic compounds together. That's how we identify it as double displacement. That's really all we're doing now, right now anyway, but that's our first step when we're given reactants like this. Identify your type of reaction. So previously we had combustion, decomposition, and combination reactions. Those all had their kind of own things. When you're given two ionic aqueous compounds, that's a double displacement reaction. So look at your reactants. That's going to tell you what reaction you've got. Second thing, we're going to predict the products. Don't forget to always charge balance your ionic compounds. Always, always, always. Number 3, you are then going to determine the state of your products: solid, liquid, gas, aqueous. And then the last thing you'll want to do is balance it. So in order to kind of completely solve a problem, as it were, we are going to do all 4 of these things. So we're going to identify the reaction type, we're going to predict the products, making sure our products are the correct ones that are charge balanced properly. We're going to determine the state of matter of all those products. So far, we've learned how to identify things as solid or aqueous. And then you're going to balance your reaction. In this case, we didn't need to balance it because it was already balanced. The other one I balanced for us. All right, so these are patterns. These are all patterns of behavior of compounds. Let's look at other states of matter. In double displacement reactions, when do liquids form? How do we know if something's a liquid or not? Thankfully for us, there are only 2 liquids we will ever deal with when we're talking about replacement reactions like these. If we form this substance, hydroxylic acid, or water. These are the only 2 liquids we see. So liquids are easy. If it's one of these 2, it's liquid. Those are the only 2 liquids. And in fact, we don't see Br2 in double displacement reactions. So we're going to see those in single replacement reactions. But in double displacement reactions, we're only ever going to see water as a liquid. And this will come from what's called a neutralization reaction. AKA acid-base reactions. And okay, that's fine for now. We're going to see there's another case where we will get water. An acid-base reaction might look something like this. These are double displacement reactions. All of these ones we're talking about are double displacement reactions. If we look at the ions that make these up, if we're to switch the two, we're going to take the positive from one, the negative from another. H plus and OH minus form water. H plus and OH minus form water. And our other one is going to just be the other ionic compound, and we're going to see that. When we see water formed, we're going to say that that's a liquid. The water formed is liquid. And the sodium chloride, of course, we're going to know as aqueous. Sodium is soluble. Anything with sodium is soluble. Anything with chlorine is, or most things with chlorine are also soluble. Our reactants, of course, are both aqueous. Double displacement reactions. So we see water as a product. If ever we see water as a product, it's going to be liquid. These often will produce a lot of heat, by the way. That's the one we saw that the temperature went crazy on. We'll talk about heat in the next chapter when we talk about thermochemistry. Acid-base reactions are going to come from an acid and some sort of hydroxide. So acids have H+, hydroxides are the OH-. We need those two to combine to form water. So in this case, we had sodium hydroxide. Could have used potassium hydroxide or lithium hydroxide or barium hydroxide, whatever. Some hydroxide and some acid. That's going to be an acid-base reaction. We're going to form water and some other ionic compound as a result. Here's another example. Again, it doesn't matter what order you put them in. I put the water first and then my other ionic compound. I could do it the opposite, or I could do it the same way. It doesn't matter. Product order doesn't matter. I could put the NaCl first and the water second. We see here again, this is acid-base because we're going to have H+ and OH- coming together. That's going to make water. Water is a liquid. The other compound we make is barium sulfate. And so, barium sulfate we may not know off the top of our heads, so we're going to have to go all the way back up. Do we have a rule for barium? Nope. Do we have a rule for sulfates? We do. Rule 3 is for sulfates. But look here. Barium sulfate is an exception that is insoluble. So, in referencing our rules, we saw barium sulfate is going to be insoluble, therefore solid. So in this case, it's both precipitation and neutralization. The reaction type is double displacement. All of these are double displacement, but these are kind of like additional types, like sub-classifications. So this one is both a precipitation and a neutralization. It's both at once, and it's totally okay for that to happen. Yes. Remember, for charge balancing, if they're the same charge, they cancel out. And if you want to review, I mean, I would check the nomenclature video for a refresher on charge balancing. That may be a good idea. So way back there, yeah. So if you need a refresher on charge balancing, that would be a good place to check it out. Because I am going to be assuming that charge balancing is not a problem, so I am going to be moving on that. All right, so we've talked about solids, we've talked about liquids, we've talked about aqueous things. The last things we have are gases, and we don't have much time. I'm going to just put them out for now, and then we'll talk about them on Thursday. So we're going to see gases in these replacement reactions are going to be ammonia, sulfur dioxide, carbon dioxide, and chlorine. Oh, we have one more, hydrogen sulfide. We've got 5. And in fact, I'm going to switch those last two because we're going to see that chlorine doesn't form in double displacement reactions, but it can in single replacement reactions, which we will talk about next time. So, but these will be things that will be gases when they're produced. And we're going to see that these first 3, these ones aren't produced directly. But we're going to see they are byproducts of some rapid decompositions. We're going to see that if we form any of these compounds, they're going to rapidly break down into gases. And water. And this is evidenced by the bubbles. We saw with the vinegar and baking soda, we saw all those bubbles. Those bubbles are CO2 bubbles. And so we will see that those are indeed gases. The ammonia is less obvious as a gas. But if you know what ammonia smells like, and you do a reaction that produces ammonium hydroxide, you will smell the ammonia. It is there. It doesn't form the bubbles like the other two do, but it will definitely do that. The H2S is produced directly. So we don't have to worry about like kind of side reactions. These first 3, though, are produced by making some other compound that rapidly decomposes. And so I'll just show you that before we end here, what that looks like, and then we'll pick this up again on Thursday. So we saw our, what did we have? Sodium bicarbonate plus acetic acid. If you do your switcheroo on these, you get sodium acetate. If we take H plus and HCO3 minus, put those together, there's our carbonic acid. Anytime we see this, it's rapidly going to break down into water and CO2. So in fact, we do not write it as H2CO3. We write it as water and CO2. Because that's what the evidence showed us. We saw when we did this, both of those should be aqueous. Sodium acetate and carbonic acid are both aqueous. But we saw bubbles, which means there's a gas there. And so experimental evidence shows us that H2CO3 immediately breaks right back down into water and CO2. So we're going to see these reactions on Thursday. We'll continue on there. All right, so this information from today is not on your exam next week. But this stuff will add up quickly too, so it's tough. Don't fall behind, because that's gonna be a bad thing. So yeah, I don't know how best to approach that. So however you study best, make sure that you don't kind of leave this stuff to the end, because this is we're gonna just keep going. We're gonna keep building on these things. So we're gonna throw in another reaction type tomorrow. And that one's going to be the most complicated of all. So we just keep on going. Alrighty, so that's it for today. I will probably post your reactions homework, but it's not going to be due for a few days, of course, obviously, until we've finished covering the topic. So, but if you want to start on it for some reason, it'll be available for you. All right. That's it for today then. So we'll see you on Thursday. So enjoy the rest of your day. Enjoy your Wednesday. See you next time. Take care.